Okay, welcome back from your break. This is still Dr. Matthew J. Traum. We are talking about material selection in your design processes and using Ashby plots to determine which materials best meet your needs. This is kind of where we left off before you guys went on your break, was talking about Ashby plot use number one, visually comparing materials to each other. And now I'm going to walk you through how to do that for a couple of examples. So remember that an Ashby plot, again, is just a scatter plot which displays two or more properties of many materials or classes of materials. And at least for this first use of this tool, we're looking for its power to visually compare materials to each other. So here's just a couple of questions. So in the class of metallic alloys, which is the lightest, and then which is the heaviest, and then which is the stiffest, and ultimately which is the least stiff. So here is, so we're going to start with the lightest. And here is our associated Ashby plot. And so again, we're just talking about metals, right, or metallic alloys. So that's just this family of kind of materials encapsulated in this red blob here. And I'm looking for the lightest alloy, which means if I have a fixed volume of material, the volume, the material that has the least density, lowest density, is the lightest for a fixed volume. So I'm going to look here on the x-axis, which is the density, and I'm going to look as far to the left as I possibly can within metals, and it looks like magnesium alloys is going to be a good candidate. So yes, okay. So I've selected magnesium alloys. I've circled it here so you can see it, and I'm going to follow this line down, and we're expecting magnesium alloys to be densities in the order of about 2,000 kilograms per meter cubed, and that's going to be the least dense of all the metals. So that's, again, just an example of how you use the Ashby chart to identify among the family of metals which one is the least lightest or has the least density. So let's go back to our set of questions, and now let's try to find the heaviest alloy. The heaviest alloy, by the same argument as lightest alloy, the heaviest alloy is going to have the highest density, because again, two metals that have the same volume, the metal with the higher density is going to be heavier, so we're going to look for the metal with the highest density, and that's going to answer the question of which of these alloys is the heaviest. So here's my Ashby plot. Again, I'm just looking at the family of metals in this red blob, and now I'm going to look all the way to the right, and it looks like tungsten here probably is my winner. Oh yes, it is. Okay. So tungsten's my winner. It's the heaviest alloy, and we're looking at something like just a little under 20,000, so maybe about 18,000 kilograms per meter cubed. So that's actually pretty interesting. There's a full order of magnitude separation between the lightest alloy, magnesium, and the heaviest alloy, tungsten, in terms of their densities within this family. But again, we got to remember that these are logarithmic scales. So even though they appear very close here, they're actually a full order of magnitude apart. Okay, so let's go back to our questions. Now we're looking for metallic alloys, the one that is the stiffest. And so for the stiffest, we're going to want the one that has the highest Young's modulus. So the one that resists deformation the most is the stiffest. So again, we're looking here in the family of metals, and instead of looking along the x-axis like we were doing before, now we're looking at Young's modulus, which is along the y-axis. So we're going to go as high as possible within the family of metals on the y-axis, and it looks like tungsten is going to be our choice again. And yep, lo and behold, it is. So the stiffest of all the available metal alloys is some alloy of tungsten, and we're looking at something on the order of about 300 gigapascals for the Young's modulus of that material. Now, what about the least stiff of the metal alloys? So okay, now we're looking for the lowest Young's modulus amongst all the metals. So let's go back to our Ashby chart. Remember, again, we're looking in the metals category, and the least stiff is going to be one that's the lowest along the y-axis. So if I cruise along here, it looks like lead is going to be my least stiff of the metals, and yep, that's what I picked. So lead looks like we've got Young's modulus on the order of maybe about 10 to perhaps 15 gigapascals there for lead. So again, there's a huge difference, right, between lead and tungsten, more than an order of magnitude, but they appear very close on this plot because we're looking at a logarithmic scale on both the y-axis and the x-axis. Okay, so that's how to use an Ashby plot to identify within a family of materials which materials have the properties that you're looking for. The most dense, the least stiff, the least dense, the most stiff, and other properties can be found as well if you have Ashby plots that are plotted for different variables. Okay, so moving on then to Ashby plot use number 2, which is the use of these plots for quantitative comparative material selection. Okay, so I'll give you guys a 4-step procedure for quantitative comparative material selection. Ultimately, what we're trying to do, though, is identify the desired attribute and then compare this attribute against real materials to find the best match. So that's sort of the overall statement of the goal that we're going for. And there's going to be kind of 4 steps that we're going to go through ultimately to achieve the best match for our desired attributes among real materials. So the first step is going to be derive what's called a value index. The second is going to be a screening process where we apply attribute limits to the Ashby chart to eliminate materials that cannot be selected because they're outside of the range of possible values. Then we're going to use our value index to rank various indices on the Ashby plots, on the charts. And then finally, we're going to make kind of a list of candidate materials and ultimately do a deep dive into other documentation beyond the Ashby chart to compare those subset of candidates against one another. Okay, so probably the best way to do this, to describe this for you, is to just go through an example of a material selection procedure tailored to a specific application. And so the first thing we're going to do is step 1 of this material selection procedure, which is to derive a value index. So we need the problem. So make myself go away here. Okay, so here's the problem. So we have a member of some assembly of parts, and it has a cross-sectional area of A. It also has a density of rho and a strength of sigma F. It's put under a tension force, which is capital F, and the length of this member, which is L, is fixed because it interfaces with other parts of the assembly on its 2 outside faces where those forces are imposed. So that length from one face to another face is fixed. Okay, and then the only other thing that I kind of want to clarify here is that by strength, this could be a yield strength, it could be an ultimate strength, but on the Ashby charts, it's ultimately the strength at which the material that you're studying ceases to be effective in opposing whatever force or whatever tension or whatever torsion you've put upon it. So it's not necessarily a yield strength or an ultimate strength. It's more just a property failure strength. There we go. Bring myself back into the scene here. So we have an additional kind of limitation on this problem. So this is our member that we are trying to find the appropriate material for, and we're told that the application requires that the assembly's weight be as light as possible. And remember, by as light as possible, we're probably talking about low density. And that the member's Young's modulus has to be less than or equal to 100 gigapascals. Not entirely clear why that requirement is given, but probably because this particular member has to be maybe less stiff than other members in the assembly, so that it absorbs most of the change in length associated with the force being imposed on it in tension. Okay, so we're asked to figure out what material selection best allows this member to carry the force F. Okay, so remember our first step is to derive a value index. Here's how we derive a value index. So the first thing that we do is, in the problem, identify the variables that we can change and the variables that we cannot change. So the variables that we can change are the cross-sectional area, right? We can make this thing like bigger in the space that it's fitting in. We can change the density, and we can change the strength, and we can change density and strength again by changing the material. The variables that we cannot change are the force that's imposed on this member, the length of the member, right, again, because it has to fit into a particular space between two other members in the assembly, and we can't change the gravitational constant. This thing presumably is on Earth and is subject to gravity. There's nothing we can do about that. So we've decided what we cannot change, we've decided what we can change, and the final thing is to identify variables that are coupled as a result of material properties. And so ultimately, we're going to want to get a ratio of these two coupled material properties. And that ratio is going to be our index value that we're going to use with the Ashby chart to make our material selection. So how do we go about doing this? Well, remember, if you go back to the problem, we're asked to find a shape, a solution, a material selection that gives us the ability to withstand this tension force that's placed on this member, but making the member as light as we possibly can. So that's not what I meant to do. There we go. Okay, so let's make this member as light as we possibly can. Okay, so the way to do that is, again, I'm interested in the force and the weight, so I'm going to just make a ratio of those two applications. With, in this case, force is in the numerator, weight is in the denominator, and it doesn't matter what order I put those in. I could flip this around if I wanted to. But remember, I'm trying to withstand this force with the least amount of weight. And so ultimately, I want to maximize F and minimize W, which means I want overall to maximize this ratio of F over W. Okay, so let's just keep that in mind that we're maximizing this ratio. All right, so I need an expression for F, because remember, F is a variable that I cannot change. So I want an expression of F in terms of some of the variables that I can change. So it turns out that a force divided by an area has units of pressure, which is also a stress. And so I can write force as just the cross-sectional area multiplied by the failure stress of this member. And then for weight, we're very good at figuring out weight because we were talking about heavy versus light materials before. So it's just a volume times the density times the gravitational constant. So the volume here is just the cross-sectional area times the length. And then the density is one of the material properties that I'm interested in, so that's good. And then G is the gravitational constant, which turns this from a mass into a weight, which is the parameter that I'm looking for. And so now that I've got these two expressions, I can plug them into my original force divided by weight ratio. So here I am plugging in the expression for force and the expression for weight. And lo and behold, the cross-sectional areas cancel out. This is a pretty interesting outcome because it means that I can change the cross-sectional area. I can make the cross-sectional area really whatever I want it to be, right? And that's not one of the variables that's constrained. That's something that we can change. This space that this member is in allows this member to basically be as big as possible in the cross-sectional area kind of aspect ratio dimension. And so the fact that it doesn't matter for this particular index is pretty interesting. We can make it whatever value we want, and it's not going to change the outcome of the ratio of force over weight. So I extract then from this combination of variables my index value. These are all the material properties that I can change. So again, the density and the ultimate strength. And then the values that I can't change, the length and gravitational constant, I just leave those alone. Those I can't change. So I'm just going to leave them alone and not worry about them. And I'm going to work on or focus on trying to, again, we want to maximize F over W. So I maximize F over W by maximizing that index value. Okay, so I'm looking at the time and noticing here that I'm just a bit over 15 minutes. So I'm going to stop, give you guys another chance to take a break, and we'll come back and pick up this problem from where we left off. See you in a bit. Thanks.